T2 star and T2 prime. We're almost at the spin echo. So T2 star and T2 prime are related to T2. Remember, T2 is the time constant which describes how quickly we lose transverse magnetization after we flip the net magnetization vector 90 degrees into the transverse plane, right? Um, so now that we understand the electromagnetic spinning top model of the hydrogen nucleus, we understand phase coherence, we can understand these related time constants of T2 star and T2 prime. So relaxation of transverse magnetization is the result of progressive loss of phase coherence between spins in the transverse plane. So that's what's illustrated in this diagram, which I borrowed from Alan Elster. Um, if you look at immediately after the 90-degree radio frequency pulse, these individual spins are in phase with each other, right? They're pointing at the same position, the same time on the clock face. And that's what happens when you deliver a radio frequency pulse at the Lorimor frequency. It's going to take the individual spins, which were previously out of phase with each other, 180 degrees to each other on the clock face, and bring them in phase with each other. As a result of them being in phase with each other, they now add up. Their transverse magnetization adds up to something. And so that's when we have maximum transverse magnetization, when there's maximum phase coherence. But over time, we're going to lose phase coherence, right? And as we lose phase coherence, these transverse components are going to start canceling with each other, right? And when they get to be 180 degrees out of phase with each other, the transverse magnetization is going to be zero, right? So it's going to gradually approach zero. So the time constant which describes that progressive loss of phase coherence, that progressive loss of transverse magnetization, it's T2 star. It's not just T2, it's actually T2 star. So T2 star is due to two mechanisms. One is T2, but the other is T2 prime. So let's talk a little bit about these time constants. So T2 is what we talked about before, but we didn't really talk about the mechanism. So T2 is due to, or it's thought to be due to, energy transfer between adjacent spins. And so the way I think about that, fluids like water are going to have long T2, right? If you look at a T2 weighted image, the fluid is going to be bright, assuming you don't suppress it with a flare or something. So the reason for that is because it takes longer for the fluids to transfer energy between the adjacent spins because they're not stably positioned relative to each other. It takes a while before they're next to each other and they can exchange that energy. That's how I think about it, at least. Whereas if you have a solid tissue where those hydrogen nuclei are fixed and they're close to each other, they're going to be able to do that spin-spin energy transfer really quickly. And so they're going to lose their transverse magnetization much more quickly, right? So that's T2. T2 prime has to do with inhomogeneity of the magnetic environment. So to explore T2 prime, let's consider two spins. So one spin, let's say, is related to a blood product. And blood products, we said, demonstrate the property of paramagnetism due to unpaired electrons in the iron atoms associated with these blood products, like deoxyhemoglobin or methemoglobin or hemosiderin. The unpaired electrons in these iron atoms within the blood products are going to augment the local magnetic field, causing these blood product hydrogen nuclei to experience an effectively stronger magnetic field strength. So if we're in a 1.5 Tesla magnet, let's say that these blood products are effectively experiencing 1.6 Tesla, whereas this water spin, this yellow one, is just going to experience the 1.5 Tesla. So if we're going to ask which spin is going to precess faster, which one do you think is going to precess faster? The blood product or the water spin? So the blood product, right? Because remember the equation? Frequency of precession is related to the gyromagnetic ratio, which is a constant, times the magnetic environment, which is a combination of the applied magnetic field, which is the same for both of them, but it's also due to the local magnetic environment, which is going to be stronger for the blood product. So the blood product is going to precess faster. So look what happens. So after the 90-degree rate of frequency pulse, right, they're in phase with each other, but after it, they're going to precess, and this one's going to precess faster. The blood product's going to precess faster, and as a result, it's going to go out of phase with the water proton. In the extreme, when it's 180 degrees apart, it's completely out of phase, and so that loss of phase coherence is going to lead to loss of signal, loss of transverse magnetization. So there you go, T2 and T2 prime. So this is a graph which summarizes this. Essentially, T2 star contrast is really what happens when you deliver the 90-degree radio frequency pulse and you don't do anything else. The loss of transverse magnetization is really described by T2 star, not T2, like I talked about in part 1. You can have the transverse magnetization curve decay according to just T2, but in order to do that, you need to correct T2 prime. And how do we do that? We do that with the spin echo. The spin echo. So how do we generate a T2 weighted image? I just kind of spoiled it. We correct T2 prime with a spin echo. So what is a spin echo? So a spin echo results from delivering a 180-degree radio frequency pulse at TE over 2. So same graph, but now we're just adding the spin echo, right? The spin echo results from putting this 180-degree radio frequency pulse at TE over 2. And just to relate this to what we were talking about earlier in part 2 of this course, so we're talking about the 180-degree radio frequency pulse. If you put it at the beginning of the pulse sequence, what do you get? You get inversion recovery, right? If you put it in the middle of the pulse sequence, you get a spin echo, okay? So, so here's an animation that I got from Wikipedia, and I'm going to try to correlate this animation with this graph, okay? So, okay. So after the 90 degree, so when we flip things 90 degrees, right, we're going from 0 transverse magnetization to 100% transverse magnetization. So this is just a review from before, but we understand why this is happening now, right? Because when we deliver a radio frequency pulse at the Lorimor frequency, right, what are we doing? We're essentially putting the individual spins that were previously out of phase with each other, we're putting them in phase with each other. And as a result, we get transverse magnetization. So we have maximum phase coherence right after that 90-degree radio frequency pulse. And that's actually represented in this animation here, right? Because the individual spins are pointing at the same time on the clock, right? They're right next to each other on the circle of precession. Fine. So then after the 90-degree radio frequency pulse, what happens? They start going out of phase with each other, right? So why are they going out of phase with each other? 2 reasons, right? One is T2, spin-spin energy transfer, but the other is T2 prime, inhomogeneity of the local magnetic environment. So whenever you have loss of phase coherence for both of those mechanisms, you're going to be on the T2 star curve. Because remember, T2 star is due to both T2 and T2 prime related dephasing. Fine. So we're undergoing T2 star dephasing, essentially, after that 90-degree radio frequency pulse. Things are going out of phase with each other. But then what do? We deliver a 180-degree radio frequency pulse. So why would we do that? The reason we do that is because it's going to put the faster moving spins behind the slower ones. So let's just revisit the blood product and the water spin, right? So the blood product is at 1.6, the water spin's at 1.5. The blood product precesses faster than the 1.5. But then what do? We give a 180-degree radio frequency pulse. So now we've put the faster moving spin behind the slower one. So now what? Watch what happens. The faster moving spin is now going to start catching up with the slower moving spin, right? So essentially, whatever loss of phase coherence that was happening in the first half of the pulse sequence, we're correcting that, right? So that's what the 180-degree radio frequency pulse does, and that's what the spin echo is. The 180-degree radio frequency pulse at TE over 2 generates the spin echo, essentially recovery of phase coherence. And why is it called an echo? So what is an echo? When you shout into a cave, right, you hear your own voice when you originally shout, and then there's a pause, and then it reflects back off of the cave and then comes back at you. Not quite as loud as when you initially heard yourself, but your voice kind of fades and then it comes back, right? So that's kind of what's happening with the spin echo, right? So you're losing signal is at a maximum, right? It starts to decay, but then after this 180-degree radio frequency pulse, signal starts to come back again, right? So that's the reason that it's called an echo, okay? So, so the faster moving spins are placed behind the slower moving ones, and they start catching up with each other, and they're going to basically perfectly catch up with each other at TE, right? And that's not an accident. We designed it that way. So by putting the 180-degree radio frequency pulse exactly halfway between 90 and TE, right? Look what happens. Whatever dephasing happens in the first half of the pulse sequence, we're going to correct in the second half at TE. So we're correcting T2 prime only at TE, right? That's how the pulse sequence is designed, and that's where we're measuring the signal. So that's the most important place to correct it. So what's going to happen, right? So that's what's happening. That's the spin echo, right? When we're recovering signal because the faster moving spins are catching up to the slower ones, right? But then after TE, what's going to happen? So the faster moving spins, right, the blood products, are going to pass the slower moving spins because they're still experiencing that 1.6 Tesla magnetic environment. So phase coherence is going to progressively decrease again, and therefore transverse magnetization is also going to decrease. So that's what's happening after TE. So we're only correcting T2 prime at TE. That's an important point for the spin echo. All right. So a T2 star weighted image has no spin echo to correct T2 prime. And a T2 star weighted image, it's sometimes referred to as a gradient echo image, a T2 gradient echo. And so I'll explain it later in the course, but essentially you can think of pulse sequences either being spin echo, they have that 180 at TE over 2, and if they don't have that, then they're a gradient echo sequence. All right, so compared with the spin echo, the gradient echo sequence has no 180-degree radio frequency pulse and demonstrates T2 star dephasing, right? So that's the correction to part one, right? So we're not losing transverse magnetization just because of T2. We're also losing it due to T2 prime, inhomogeneating the local magnetic field. All right, so that's what's happening in a gradient echo sequence. And the gradient echo sequence, right, the time constant which describes the loss of transverse magnetization, the loss of phase coherence, it's T2 star, because T2 star includes not just T2, but also T2 prime. A spin echo sequence, right, that's going to correct T2 prime at TE, right, which is when we're measuring the signal. So the spin echo sequence, if you're going to describe the graph that it's going to be on at TE, it would be really following the T2 curve, right? But you need a spin echo to have T2 dephasing. So that's why those answers are incorrect.